Welcome to the Bare Essentials of Research for Students. My name is Arangan Lingam, and today I'll be giving a talk titled Introduction to Medical Statistics. The goal of today's talk is to introduce students to medical statistics available in research and literature. However, I will not be covering how to perform statistical analyses. The outline of this talk is as follows. I'll be discussing the role of statistics and its limitations. I'll do a brief overview of different variable types, and then move on to discuss descriptive statistics, including frequency tables, measures of central tendency, and measures of dispersion. The next topic will be inferential statistics, including confidence intervals, hypothesis testing, and two examples of very commonly used statistical tests, which are the student's t-test and the chi-squared test. The role of statistics. Statistics are an incredibly useful tool to help you objectively assess your results and support your conclusions. However, they suffer from a number of limitations. They're heavily reliant on good study design and are very vulnerable to bias in methodology. Thus, higher levels of evidence in study design will limit bias in statistical results. To illustrate this further, on the right I have the levels of evidence pyramid, with the top of the pyramid being systematic reviews and randomized control trials. These are the top of the pyramid because based on their study design, they limit bias more so than the lower studies. Cohort studies and case control studies, although are very powerful, are more prone to bias. Therefore, it's very important to always consider the statistical results in the context of a study design, because if the study is a higher level of evidence, the statistical result is, and the conclusion that can be drawn, is more reliable. The other thing I want to mention is that statistics only suggest relationships. The researcher must show a plausible scientific explanation, a temporal relationship, that is, a relationship between the variables based in time, and a dose-dependent relationship between the variables. These are necessary to again support the researcher's conclusion. Now I'd like to do a brief review of variable types. There are independent and dependent variables. The independent variable is the variable that we control or change. The dependent variable is the variable that we measure. So in the question, does smoking cause lung cancer, smoking is the independent variable and lung cancer is the dependent variable. Another organizing system for variable types is based on the type of data we collect. There are categorical variables and interval variables. This distinction is made on whether we know the distance between data points. So in an interval variable, for example weight, there is a set distance between any given point that we understand and know. On the other hand, in a categorical variable, there is no known set distance between data points. The categorical variable can be further subdivided into nominal and ordinal. Nominal is when there is no natural order in the variable, as well as not having any set distance between data points. So an example of this would be gender or race. Whereas in ordinal, although there's no set distance between data points, there is a natural order. So an example of this is a pain score. And although the pain score 1 to 5 is numeric, we need to be careful not to get confused with an interval variable, because the difference in a 1 to 5 pain score of the difference between 1 to 2 is not necessarily the same as the difference between 4 to 5, hence demonstrating that we don't have a set distance between points, but there is a natural order. So moving on to descriptive statistics. Descriptive statistics are used to describe our data. And depending on the type of variable, there are different ways in which we can describe our data. For categorical variables, the most useful way is a frequency table. So the frequency table is fairly straightforward in that it simply describes the frequency and percentage of the data point we collect. So this is a frequency table of a study done looking at types of anti-clotting medication that 10 patients are on. So we have a total frequency of 10, that's our sample size, and the drugs they're on. So for example, 2 patients are on clopidogrel, which makes 20% of the total sample size. Descriptive statistics for interval variables are slightly more complicated. Because interval variables are numerical and there are known distances between data points, it allows for more options with regards to describing. Frequency tables can still be used, however the preferred method tends to be measures of central tendency and measures of dispersion. Measures of central tendency are essentially measures to try and describe where the middle of the data is. Now there are three ways to do this. Mean, which is the arithmetic average, median, which is the middle of a data set, and the mode, which is the most commonly occurring value. All of these attempt to describe the middle of a data set in different ways. So this is just to illustrate the difference between mean, median, and mode. We have two data sets here, data set 1 and data set 2. As you can see just immediately by taking a look, data set 2 is more spread out than data set 1. This will result in differences between the mean, median, and mode. So, as we discussed in the previous slide, mode is the most commonly occurring value, denoted here by the red line. The median is the middle data point from the entire data set, which is the green line. And the mean is the arithmetic average, which is where you add up all the data points and then divide by the total sample size. So as you can see, mean, median, and mode are all effective ways to describe a data set, however, differ greatly based on the spread of the data. Measures of dispersion. Measures of dispersion are essentially a measure of how spread out data is. Now we describe the spread of data in two ways, using variance and standard deviation. Mathematically, variance is the average difference of all the data points from the sample mean squared, and standard deviation is the square root of the variance. But the take-home message here is that both standard deviation and variance describe how spread out data is, and the greater the standard deviation, the more spread out the data set. Often in studies you'll come across the term one standard deviation or two standard deviations, and what's being discussed in that situation is that 68% of the sample data falls within one standard deviation. So if you can think of this as a set of data plotted onto a graph, 68% of the data points will fall within one standard deviation, and 95% will fall within two standard deviations. So how does this translate to actually being given a specific value for standard deviation? This is the sign for standard deviation. Now remember, this is dataset 1, dataset 2. So dataset 1 standard deviation is 0.25 and dataset 2 standard deviation is 1. Now, as I mentioned earlier, you can immediately see that dataset 2 is more spread out, which is shown by the fact that the dataset 2 standard deviation is 4 times larger than dataset 1's. What the standard deviation actually means is that if we take a look at the mean value, it's a little bit higher than 1. 68% of the data in dataset 1 will fall between 1.25 and 7.5. So between here and here. Whereas in the second data set, we have the mean, it's roughly 1.65. 68% of the data in the second data set will fall between about here and all the way over there. So much more spread out. So moving on to inferential statistics. Inferential statistics are designed to support conclusions beyond what's shown in the immediate data, thus inferring. So in this section, I'll be discussing confidence intervals, hypothesis testing and p-values, and the two statistics examples being the student's t-test and the chi-squared test. So before discussing confidence intervals, we must understand the difference between a population and a sample. When we conduct a study, it would be ideal if we could study everyone in our population of interest. However, that's not usually feasible, so we take a small group that we think is representative of that population and study them. This small group is what we refer to as our sample. Now, when we study this sample, we get results, we base some conclusions based on this sample, and we try and extrapolate these conclusions onto the population. And there are some errors associated with this. So when we find a sample mean, we want to try and determine what the population mean is. And confidence intervals are a way that we use to estimate the population mean from sample parameters. So what we do for this is we use sample information, parameters from our sample being sample mean, sample standard deviation, and sample size, and use a confidence interval calculation to try and estimate what the population mean is based on that sample. So this is an example of a confidence interval being used. We're interested in how much television students watch at a particular university. So we take a sample of 10 students from this university and ask them how much television they watch. So we have a sample size of 10. We have a mean of 5.5, meaning that on average, or on the arithmetic average of television watched per day for this group of 10 is 5.5 hours, and a standard deviation of 3. Now remember, this standard deviation means that 68% of the sample watch between 8.5 and 2.5 hours of TV per day. So, using this and plugging it into our confidence intervals formula, which I won't be covering here because it's beyond the scope of this lecture, we're able to produce a confidence interval. Confidence intervals can be at a range of confidence. In this situation, the sort of standard is to use a 95% level of confidence. When you read a paper, it'll look like this. We'll get a 95% confidence interval that the population mean lies between 3.3 and 7.7. So what this means is we are 95% confident that the mean hours of television students at this university are watching lies between 3.3 hours per day and 7.7 hours per day. So the important thing is to be able to interpret a confidence interval. I'd like to discuss hypothesis testing next. Hypothesis testing is used when we're trying to compare groups. So in the situation we're comparing means between two groups, the null hypothesis is that there is no difference between the groups. The alternative hypothesis is that there is a difference between the groups. And generally, when we do statistical tests, we're trying to find either evidence for or against the null hypothesis. This ties in quite well with p-values, which I know is quite a feared term among students. The p-value is simply the probability that the observation is caused by random chance. So, for example, we have a group that smokes and a group that doesn't smoke, and we're interested to know whether there's a higher incidence of lung cancer in the smoking group. Based on our observations, we have seen that there's a higher incidence of lung cancer in the smoking group, and we've run a statistical test. And the result from the statistical test tells us that there's a p-value of 0.05. This means that there's a 5% probability that this observed difference is due to random error and is not true. So if there's a 5% probability that this observation is due to random error, then this means there's evidence against the null hypothesis. Because if there's only a 5% chance that there is no difference, then the alternative hypothesis is more likely. So how did we come to this p-value? This leads us on to statistical tests which we use to compare groups. I'm talking about two examples today, the student's t-test and the chi-squared test. The student's t-test and the chi-squared test are used to compare groups, but the choice of statistical tests is usually dependent on the outcome you're looking for, as well as the type of data. The student's t-test is used when there's one independent categorical variable, being the group, and one dependent interval variable, for example, weight. In the chi-squared test, we use this test when there's one independent categorical variable, being groups, and one dependent categorical variable, for example, drugs names or colors or gender. So the chi-squared test is used normally in situations where we have a lot of categorical variables and we're using frequencies to describe our data. So discussing the student's t-test first. I have an example to try and illustrate this, where we have a low-fat diet intervention, where Group A is on a new low-fat diet and Group B is our control group on a normal diet. Each group has a sample size of 10. The mean weight in Group A is 71.9 kilograms, whereas in Group B it's 90.7 kilograms. So immediately we can see a difference in weight. However, we can't be certain if there's a true difference between the two groups, or it's just based on random chance, or due to small numbers, or any other number of errors or bias. The standard deviation in Group A is greater. So we run a student's t-test for the equality of means, trying to determine if the means between these two groups is equal. We know that the mean difference is 18.8, and student's t-test gives us a figure, a p-value of 0.006. What this means is that there is a 0.6% chance that the difference we've observed between these two groups is due to random chance. So this is evidence against the null hypothesis, and thus is supporting the alternative hypothesis, which is that there is a difference between the two groups. This is an example of a chi-squared test. So the question here is there a difference in anti-clotting drugs prescribed between two hospitals? So we have Hospital A and Hospital B, and we have 15 participants from each hospital. These participants have been surveyed to see what anti-clotting drugs they're currently on. So in Hospital A, we have 3 on aspirin, 1 on clopidogrel, and 11 on warfarin. Whereas in Hospital B, we have 1 on aspirin, 11 on clopidogrel, and 3 on warfarin. So we have roughly a frequency table here and the chi-squared test being performed. Now again, the chi-squared test is looking at whether there's a true difference between A and B, or whether these observed differences are due to random chance. The p-value we've received is 0.001, meaning that there's a 0.1% chance that the difference we're observing between these two groups is due to random chance. Thus, again, there is evidence against the null hypothesis and evidence for the alternate hypothesis, being that there is a difference between these two groups. So just to summarize what we've discussed today, we've discussed the role of statistics, including its limitations, and done a quick review of different variable types. We've gone into descriptive statistics, including frequency tables, measures of central tendency, and measures of dispersion. We've then gone on to discuss inferential statistics, including confidence intervals, hypothesis testing, and given 2 examples of a very commonly used statistical test, being the student's t-test and the chi-squared test. Thank you very much for listening to this online lecture. Please share this with your fellow students, and do post any comments if you have any questions, concerns, etc.